Okay, so this week, rather than doing a simulation, I decided to do a lab dedicated to just doing some free body diagrams and setting up equations of motion. And I decided to do a couple examples first. So you should have gotten the download from the website. Let me grab mine. And let me ask you if it looks something like, share screen. Okay, so you should have something that looks like this. Everybody have something that looks like this?
No, I don't have access to the lab document. All I was able to get access to was the instructions.
Okay, the instructions, okay, when did you try?
During our break before lab started.
Okay, did anyone else try to go to it?
I'm in the labs section now, and all it says was lab 7 due October 6 instructions. There are 5 questions on this lab, but there's nothing to click to take a look at like what you're showing.
Okay, let me go see what you're seeing. Hang on a second, because maybe we're seeing it. I want to make sure that I want to make sure that everyone's seeing the right thing. Okay, I'm going to go into under assignments. So you have something that looks like this, or did you go to?
I went to modules, and then when you go to modules, it says labs. Clicks labs week 8, free body diagrams, and it says week 8, September 29th, lab 7 free body diagrams, and then it has a Wednesday, October 6th. It says instructions. There are 5 questions in this lab, but it doesn't have anything to click.
Okay, let me reset this. Hang on a second. Something happened here. So let me reset this. I don't know why this is, because that should not be happening that way. Maybe labs. You're doing a submission type. Oh, I see what I did wrong. I'm sorry. Let me fix that. Okay. I see what I did wrong. You would have got it fine through the other way, but supposed to get it done correct both ways. So give me 1 second here and you'll have it fixed. Okay. I hope this works right. Oh, hang on a second. You know what I'm doing wrong. I didn't put the link I put the link to the assignment, but not, then I didn't put in that assignment. I didn't put the link to the to the file itself. Okay, would you try again?
All right. Yeah, that's there.
And then Araceli, are you able to get it now?
Yeah, I see it.
Okay.
Yeah, yes, I see it as well.
Yeah,
All
me
right.
too.
Apologies, well, I too make mistakes. Is all I can really say. Okay. So there's 5 questions, but what I have also at the front is 2 examples that we're going to work out here. Now, I wrote the whole question down because I, got these questions out of things, but we're not going to work out the whole question. You see down here, all I ask you to do is to do the free body diagrams and set up the equations for motion. Okay, so I want you to set up the free body diagrams for every object and to set up the equation of motion. You're going to need to do each of those. I'm going to do a couple of examples first. Example 1 and example 2. Some that are a little bit more difficult. Okay. Now, especially the second example is more difficult. So let's start with the first example. Okay. Now this was a solid uniform ball of 45 kilograms diameter. Okay. And then it asks you to get how hard. I don't need you to care about how hard. We're just going to do setup of Newton's equations of motion. I'm going to stop there. If you want to work the rest of the way out to actually solve it and see if you'd solve the rest of it correct, I'll give you the answers there. But I'm just going to set up Newton's equations of motion for an arbitrary mass, and we're going to set the angle here. So what we have is we have a ball of diameter 32 centimeters. That we need to keep, okay? It's against a vertical frictionless wall by a thin 30 centimeter wire of negligible mass. And it's 30 centimeters to the point at the ball. So it's a 32 centimeter. So let's start drawing this equation here. So first off, let's try to redraw this diagram a little bit. Sometimes I just like to redraw it just to get my bearings on it. Here's just a circle. This here is 16 centimeters. Here we have 30 centimeters to here and 16 centimeters to here. So it's 46 centimeters from this point to this point. And this has some angle phi. Okay, so I just redrew the diagram a little bit. You could also just go 16 centimeters here, and it's 16.0, and 16.0 centimeters here. Okay, now I redrew it here so I have an angle. This has some angle. I'm not quite sure what that angle is. But what do I know if I want to draw the free body diagram? First off, I have my, let me do my free body over here, free body. I only have one free body in this problem. There's just one free body. But there's a real tendency when people get this to think that the wall is pushing up this way. And the wall is not pushing out this way. The wall is pushing normal. This is tangent. Okay, so the wall is going to be pushing normal. So I've got my X and Y coordinate system. Here's my ball. I'm just going to represent it by a much smaller ball. Okay, it's got a force T, and I drew this kind of long. Okay, and it's got its weight W. I'm going to draw in a dotted line here and a dotted line here for my X and Y axes. So this angle here is also phi. That's the same as that angle there. They're opposite angles. So if this was phi here, this is phi here. Okay, so that's the free body diagram right here. Okay, with just T. And then this also has a normal force, N. So I didn't write the vectors over and everything else, but that's your free body diagram. Okay, now there's now that's part one. So if you look at this, if I had this one in here, I'd written like this, you know, that would be set up the free body diagram for each object. Well, my only object is this. Okay, I only have one object, the ball. Now, Newton's equations. Okay, my sum of my forces in the X direction. Well, this is my positive X to the right. So it's going to be T. And note, this is where I've defined my phi. I've defined phi with respect to the y-axis. So my X is sine. So it's going to be T sine phi minus N is equal to MA sub X, which is equal to 0. And my sum of my forces in the y direction is going to be T cosine phi minus, well, I can put W or I can put mg, whatever you prefer. We'll put W is equal to MA sub Y, which is equal to 0. Or this is equal to T cosine phi minus mg equals 0. Okay, that's all there is to it. We did the one object and the sum of the force in the X and the sum of the forces in the Y. And the object isn't moving. So this sets up the problem. Now you can go forward and solve for each of these. Okay. And you can go forward and solve for each of them, but this is where you finish the lab. I want you guys to practice on setting up the problem. These are your equations, okay? I have mg here. I've got t is an unknown. I have a normal force as an unknown. Both the accelerations are 0. M and G is known. So T and N are unknown. I have 2 equations and 2 unknowns. I have, if I wanted to write down my equations to then solve for doing this, I have T sine phi minus N equals 0, and T cosine phi minus mg equals 0, okay? T and N. Now, you might argue that you don't know phi, but you do know phi because sine, L sine phi, some arbitrary L, and we're going to call this L. This distance here is what I'm going to call L. L sine phi is equal to 16 centimeters. Or sine phi is equal to 16 centimeters divided by 30 plus 16, or 46 centimeters. So you can get sine phi there, all right? So if you have sine phi, you can calculate phi. So phi, you know as well. And so you have 2 equations, 2 unknowns. Phi is equal to the arc sine of 16 over 46. Okay, so you've got everything you needed. That's the easy one. Now, let's take a look at the second example. This example is a lot trickier. Okay, again, I'm just going to set up the equations. I can give you a little bit of what the answer looks like, but the answer gets fairly complicated in solving the math. Again, solving the equations and solving the math is just taking the care in doing it. Setting up the equation is tricky. So first, I have a question for you. Put chat on so I can see if anybody's answering. So first, I have a question for you. How many free body diagrams do you think I need in this problem?
3.
3? Anybody
no,
else
4.
have an answer?
5.
5?
2.
2? Anyone else?
I say 3.
And another 3. Well, I say 4. Okay. This pulley, I don't have to worry about. It's not moving. It's stationary. It's just a pulley. This pulley is going down. This mass and this mass are moving, and this mass is moving. So I've got 4 moving objects in here. Now, when we get to moments of inertia and other things, I'd have to consider this pulley as well, because it'll have a moment of inertia. But right now, we're taking these as massless pulleys. But this massless pulley is still moving. Even though it's massless, it's moving. Now, you can break up this problem in multiple ways. I could treat this as one more familiar where I have all this mass, M1 plus M2, and M3 on this side to just figure out how M3 is moving, okay, with respect to M1 plus M2, or I could break them out. Now I put on this that I want all the free body diagrams. There are ways to simplify the problem as you move through, but I want all the free body diagrams. So I'm going to do the free body diagrams for each of these. And I'm not going to put in my acceleration vector first. First off, I'm going to choose a coordinate system. And I'm going to choose my X and Y. Okay, Y being up. Now, I have no idea which way any of these masses are accelerating. If M1 plus M2 is less than M3, it's going to be accelerating. This system is going to be accelerating up, and this one's going to be accelerating down. If M1 plus M2 are heavier than M3, then M3 is going to be going up, and these two are going to be going down. Okay, I don't know which way they're going. Okay, one of them is going to be, this pulley is either going to be moving up or moving down. Okay, this block is going to be moving in the opposite direction of this pulley. That's really all I know there. So I'm going to do 4 free body diagrams. I'm going to do object 1. Here's object 1. I have here's rope or line A. Okay. So it's got line A attached to it, string A. So I have T A, and I have down W1. I'm not going to write in my acceleration at this point. I'm going to leave acceleration out of it, and I'm just going to assume they're all going up at this point, which we know isn't what's happening. Okay, now we're going to have to take some of that in light of, but I'm going to set Y as my positive direction. Okay. Number 2. This was box 1. Number 2. I have TA, and I have weight 2, which, by the way, is, remember, this is M1G. This is M2G. Number 3. I've got 3. I've got W3 down, or M3G. And I've got TC up. Okay. And object B. I'm not going to write 4, I'm going to write object B because that's how it's labeled here. I've got my pulley B. I'll do it as a circle just for fun. And I've got TC up. And I've got TA down. And I got TA down. Now, I'm gonna go ahead and write in WB equals MBG, but this equals 0 because we're dealing with a massless pulley. That equals 0. Okay, if it wasn't massless, we'd have yet a different problem. Okay, but I wrote it in here just for fun. This would be fine for you to do the free body diagram, but note that that's 0. Now, all my sum of my forces in the x direction are 0. This is only moving in the y direction. So my sum of my forces is here, T, A, minus the sum of my forces in the y direction for this one is equal to TA minus M1G equals M1A1. I'm not putting a sign value in here yet. Okay, I'm just saying it's M1A1. We're going to end up with negative or positive signs depending on the masses. Okay, so this is number 1. Number 2, my sum of my forces in the y direction is equal to TA minus M2G is equal to M2A2. Number 3, my sum of my force in the y direction is equal to TC minus M3G is equal to M3A3. MB, sum of the force in the y direction is equal to TC minus 2TA. Note, this is 0, so I'm not even going to bother putting in there, is equal to MBAD, which is equal to 0. Okay? So there's 4 equations, right? But how many unknowns do I have? A3, A2, A1, TA, and TC are all unknown. M1, 2, and 3 are considered known, but I have 1, 2, 3, 4, 5 unknowns. I only have 4 equations, so I got to have another unknown, right? You need to come up with another unknown for me. So what's one thing that I know? Okay. If I were to draw acceleration vectors, and I don't really want to draw acceleration vectors, but I'm going to assume that 1, 2, and C are going down. I'm just going to draw that this is A1, A2, AB. They're all going down. I don't know that to be true. They could all be going down. C and or B and 1 might be going down and 2 could be going up. B and 2 could be going down and 1 could be going up. They could all be going up. But what I do know is 3 and pulley B are going in opposite directions. So I'm just gonna write this up for right now. I'm gonna keep these all as positive though at this point. Okay, I'm not gonna put in the sign factors in here yet. Here I put in the sign factors for the direction of the forces, and I'm gonna let the sign come out of these. Okay, because I really don't know what, it's getting to enough things that I just don't know exactly what's happening. I could make assumptions, and then whatever I put in here, if I get a negative, and then write out my equations, assuming everything is positive, and make that assumption. And then if it comes out with a negative number, it just means I chose the arrow in the wrong direction. But what do I know for sure? I know that A3 is equal to minus AB. If this guy is going up, this pulley is going down. If the pulley is going, if the block is going down, the pulley is going up. That's one thing I know. So I know that AB is equal to minus A3. That's one thing I know. But that doesn't really help me because now I could put in AB in here, but I still have an unknown. So I still haven't gotten to 5 equations and 5 unknowns. And that's what I have. If I have 5 unknowns, I need 5 equations. What's the other thing I know? And this is a little bit more complicated to just see, obviously, but this guy going down at an acceleration, it's just equal to the average of these two's acceleration. I don't know the signs of the acceleration, but it's equal to the average of their 2 acceleration. If these guys are the same mass, now to try to convince you that if these 2 are the same mass, then this won't be rolling at all on this pulley. So if I have this acceleration plus this acceleration divided by 2, it equals this acceleration, right? If they're the same mass, this won't be moving on the pulley, right? Trying to convince you. So then acceleration of the pulley just equals the acceleration of this mass, acceleration of the pulley equals this mass, and their average acceleration equals their own masses. Okay, if this one's going down at, say, 2 meters per second, and this one's going up at 1 meter per second, then the whole system is going down at an average of that acceleration. So the acceleration of B is equal to the average of the acceleration of 1 and 2, which is just 1/2 A1 plus A2. Or I can write 2AB is equal to A1 plus A2. Or A1 plus A2 is equal to minus 2A3. So now I can put in a final equation unknown in here that A1 plus A2 is equal to minus 2A3. So now I have A1, A2, A3, TA, TC, 5 equations and 5 unknowns. Let's write down these equations again. TA minus M1G is equal to M1A1. TA minus M2G is equal to M2A2. TC minus M3G is equal to M3A3. TC minus 2TA equals 0. And A1 plus A2 is equal to minus 2A3. Now, I'm not going to continue on and do them solving all the expressions. Let me see if I've got, I did do A3. Now, again, it's going to depend on the masses and the sign and what you choose for your coordinate system as positive and minus. So you can come out with the opposite of this, basically a negative sign. But if you work through the math, and like part A asked me to get the acceleration of the block of mass 1 first, or mass, I think the acceleration of block of M3 first. For part A, so the acceleration of block M3. So we can write A3. I'm going to tell you, if you want to work these out, is I came up with 4 M1 M2 minus M3 M2 minus M3 M1 divided by 4 M1 M2 plus M3 M2 plus M3 M1. And times G. Now, I should be able to do this a little bit easier than this. Okay, and I could have probably just put M1 and M2 as a joint mass and their combined acceleration. So there's some other ways we could have simplified this further. But this is your A3. If you want to go through, this is all the places I'm asking you to stop on. This is really the only place I'm asking you to stop and ask you to stop on the problems that I gave you in the lab. This, I should have asked you to give me things there like the relationship of the accelerations, the relationship between the free body diagrams. Because this gives me the 5th equation. This gave 4 equations and 5 unknowns. I still needed that relationship between the accelerations to get a 5th equation to handle the 5th unknown. Here's my 5 equations and 5 unknowns. 5 equations and 5 unknowns. I'll be honest, had I worked out the problem and had enough time to modify the assignment beforehand, I would have asked you to make sure to identify the relationships between the motion of the objects, such as their accelerations are equal but opposite in sign, or things like that, and make sure that you had the same number of equations as you have independent equations as you had unknowns. But all I asked you to do was to set up, write out the ones with the forces. That's not now. In the case, for instance, these just had forces in the Y. I didn't have an X direction, but I had 4 different objects to deal with. Our cover page. This had 3 objects to deal with. This has the 2 objects, MA and MB. This, and I wanted to find the tension in C. one of my reasons for doing this is I've done a problem like this before. And the biggest problem I've seen with students, I did this on exam, and the biggest problem I saw with students on the exam was setting up the free body diagram to start with. And we needed to find the tension in C. Wanted to find the tension in this cord. The tension in this cord, the only force acting on this massive pulley was the tensions in this cord, which were equal. You had to work back, you had to work to find the tensions in the cords to find the tension in C. But you need to set up your free body diagrams. Okay. Here are your free body diagrams here. Here we have set up the free body diagrams for each object along each axis. Okay, so you have normal forces for your free body, but some of your force in the y are going to be 0, which is what you're going to do to then define the force of friction. So you have the sum of the force in the y being 0 in each case. Okay, assume as friction between all surfaces is present and the coefficient is different between the different surfaces. That is, the coefficient is different between A and B, and the coefficient of friction between the horizontal tabletop and B is different. Here, we're applying a force on a block. Okay, you need to do the free body diagram. Now, assume friction is present between all surfaces and the coefficient of friction is different between each surface. Recognize you have a force applied here. You have capital MG down here. You have the force of friction opposing motion going to the left. You have a normal force from the table to the mass here. You have a normal force from the little mass pushing on M here. And hence you have a force of friction from the little mass pushing on M this way. So this mass is acting on little m, is acting on big M. Big M is also acting on little m. So the free body diagrams might just be a little bit more complex than you think. But you need to make sure you include the fact that you have this applied force, you have the normal force from the table, and hence a friction force that had, because in the coefficient of friction here is different than the coefficient of friction here. You do not have the normal force of big M acting on little m. You have the normal force of little m acting on big M, and you have the force of friction of little m acting on big M. Okay? Just as, and that could be this way, it may well be this way acting on big M. If you choose your friction direction wrong, you'll get a negative sign when you work out the problems if you keep it all straight. Okay? But write out the problem. Now, you need to make sure that you show the force of friction on little m is opposite in direction of big M. Now look what that means. It's going to be, you'll have a force pair, for example, the normal force from big M acting on little m is equal and opposite in direction of little m acting on big M. So those are force pairs because it's not going through either way. You also have the friction of big M when it's acting on little m. That's a force on little m. And you have friction of little m acting on big M. Those have to be moving in opposite directions. And it's not obvious that little m would be sliding down the plane or going up the plane. And in fact, this problem comes out of a problem asking, with what force do I make sure that it doesn't slide down the plane, for example, or doesn't, or also doesn't move up the plane? What is my range of forces? Because if I push this bottom part hard enough, little m will go up the plane. If I have low friction here and I don't push it at all, it'll start sliding down the plane. Okay? If there was no friction here, there's one force I can push at that'll keep this perfectly on the plane. Okay? You need to look at this normal force here. Okay? That normal force is that mass pushing on little m. They get matched. If you need to draw out the free body diagram for this, it gets a bit more complicated than you might think. Okay. Here's a couple other ones. I've got two masses and a rope between them. Okay, again, you have mg acting, you have normal forces acting, you have tension in the rope. This tension is the same on both sides. But draw the free body diagram. You don't need a free body diagram for, in this case, the inclined planes or the pyramid here. You just need a free body diagram for MA and MB. Those are the only objects of interest. In this case, your object of interest is my big M and my little m. Over here, you need 3 free body diagrams. Okay? The tension at the bottom of this rope is not the same as the tension at the top of this rope. You're only going to care in the end about the tension at the bottom and the tension in the top, but they're not the same. Unlike all our chords, most of the chords we've talked about, if not all the chords, this is not a massless rope. It has weight, a distributed weight along it. You should still be able to figure out what the tension is at the top, and the tension at the top, and the tension at the bottom. Think about the fact, I could ask you to find the tension everywhere in between, but think about the fact that this picture here, okay, I want you to think about the fact that this picture here, when you're thinking about the tension at the top and tension at the bottom, isn't a whole lot different than so we have 1, 2, 3. Mass 1, the rope, mass 3. Okay, if I had massless ropes, okay, the tension right at the very top is like that very last little tiny bit. And then the tension right at the bottom is the very last little bit at the bottom. So you know if I had 1, 2, and 3, then this tension A and this tension B would be different. Okay, well, that's really, you can think about it this way. So think about what a problem with a mass of a block of mass M means. Don't give me what block 2 is, but give me, a rope and what T top is and T bottom is. Okay, so there is a hint on that one, but you need a free body diagram for that one. There are 3 objects, 1, 2, 3. If this was massless, I'd only have 2. Really the same as this, where these are now massless. Okay, so just think about how you would do that. Okay, and a free body diagram and equation of motion for this. Assume friction is present between all surfaces and the coefficient of friction is different between the surfaces. Yes, that can be true. This can be one surface, but I could have a block with Teflon on one part and sandpaper on the other one. Write up your free body diagrams, assuming the tension, the friction here is different than the friction here. So when you write up the equation of motion, they're different. Okay, these are all fairly straightforward. Okay, this one's a little bit, this one has angles in it, so you gotta work through that. This one's a little extra tricky because there are a bit more forces than you think. So go through it and think about, what does this guy feel? Okay, he feels a normal force. So take a look at these and set up all your equations. Draw in the forces on your free body diagrams. All right? So everybody clear out what we're doing with this?
Yeah.
Okay, I want you guys to get practice dealing with free body diagrams and get comfortable with free body diagrams and setting up your equations of motion. Because if you get there, if you don't get there now, it's gonna get really, really hard as we move on. Okay, we can get through energy, but it's gonna start to get really hard if you don't get on. And getting into, as soon as we get into angular momentum and torque and other elements, it'll get much more difficult. So I really want you to get that down. All right. That'll be all for the day now. Any questions? This is open now if you want to ask some homework questions or anything like that.
No, maybe later.
Anna, Araceli, any questions?
No, not yet.
Okay. You guys should think about bringing questions to lab. It's a good time to get my undivided attention. All right, then I will stop the recording and see you next week.
Bye.
Teacher, can you explain me the last part in the exercise number 3? Is I don't know what is the 4.
Which one here? Are we talking about this or which exercise number 3?
The double. Oh, I don't know.
Was this
The
on the
sample.
homework?
The sample 2. No, in this laboratory.
In the example 2?
Yeah. Your answer?
Oh, this answer here? Are you? Let me go back to sharing screen here.
Thank you.
I'm going to stop the recording.